Well, greeting, chemistry department. We're going to look into factors affecting solubility and the rates of dissolving different objects and things today. So we're going to start with just the idea of oil and water, and the idea that water is a polar substance, we've talked about before, H2O, and oil, a nonpolar substance. And so when we mix the two together, we can see that the oil layer is on top and the water is on bottom, and that they don't want to mix together. Now, to add to that idea, we're just going to take a little green food coloring, and if we put some on top, we're going to notice that the food coloring does not dissolve in the oil. We're going to be hearing this term like dissolves like is going to be one of the key ideas that we have throughout this. The food coloring and the oil don't dissolve together, they stay in nice little droplets. If we take and dissolve though and get that water and the food coloring to touch, it quickly starts to dissolve into the water so that we can see that layer of oil. No green, but that water is now dissolved the food coloring, so that water and the food coloring like dissolves likes, that water wants to dissolve in the food coloring, not in the oil. So that's going to be one of those ideas that we look at, oil being a nonpolar substance, water being a polar substance. Now from there, what we're going to be looking at is how different rates of dissolving occur. So I've got over on the side here, we've got some water that's been heating for a little while, and I've got some water that has a little bit of ice in the top to represent some cold water and some hot water. Now this one we're just going to take a couple minutes, so we're just going to drop tea bag into the hot water, and we're going to drop a tea bag into the cold water, and we're just going to let those two sit for a couple minutes to see how they change over time. So we've got those two just going to sit there and see how the dissolving occurs there. So we'll come back to that one. The second one, we've got our sugar cube. They're old, so we're not going to eat any of them. And I've got a second sugar cube. I've already used the mortar and pestle to dissolve and crush, or to crush into smaller pieces. The cube, and what we're going to do is just drop the cube into one, and we're going to drop another one in, and we're just going to let them sit there, and as they sit, we're going to see how that rate of dissolving changes. Now in these first two ones that we're looking at, there is the key idea that we want to see is the more collisions that we can have between the solute and the solvent, the faster that rate of dissolving is occurring. So if we look over to the hot water versus cold water, our hot water motion of the molecules, kinetic molecular theory, the faster that those molecules are moving, the more collisions they have, the more chance that solute solvent has to come in contact, the more dissolving we have, we can see that tea being made. In the cold water, molecules are moving much slower, there's not as many collisions happening, so that rate of dissolving is much less in that cold water. If we move back over to our pile of sugar on each side, we can see that the sugar cube is now breaking down, but still is a big pile. Our crushed sugar cube, on the other hand, has mostly dissolved. There's more surface area contact-wise for the crushed sugar cube versus the actual sugar cube. So more contact between the solute solvent speeds that rate of reaction, or that rate of dissolving up. Motion sickness idea. If we take another sugar cube and drop one in and drop another one, if we are to stir, agitate, or move, as we stir and agitate, break down, and move, that allows that sugar, that solute, to come in contact with water, the solvent, and it causes it to break down and to dissolve much faster. The more contact we can have between the solute and the solvent to make our solution, the faster it will dissolve. So as we're going stirring, agitating, shaking up, anything like that allows for a much quicker dissolving rate than if we just keep it just sitting there itself. So as we're working, we'll give it another good little stir just to try to move that along. And we get most of it to dissolve. We'll give it another moment, but we'll just move on so that we don't have to worry about sitting here and watching them just dissolve. But the faster that agitation, the stirring, the quicker that dissolving is going to occur. So we're going to go back with that oil and water idea. I've got A little more water in one. And in our second beaker, we're going to put a little bit of oil. Now this time we're going to look at an ionic compound. Our ionic compound of choice is just salt. And what we're going to do with the salt is we're going to take some salt and we're going to put it into the oil. And we're going to put some into the water. Now as we let them sit here, one of the things we're going to notice is that as we start to let them dissolve, that the salt will eventually, I put a lot in there, dissolve over time. Versus on the other side, our oil, we can see that the salt crystals are actually staying a very nice cubic structure. We can actually see that crystalline structure. And over time, that salt will dissolve, but in the oil part, it will not. We'll give that salt just a little bit more stir in the water, see if we can get it all to dissolve in before moving on. I set this up earlier. This is actually salt from yesterday with oil. And even after sitting there for an entire day, those salt crystals, you can see that nice cubic structure of the salt still hasn't dissolved in the oil versus in the water. It's basically almost all dissolved already. So idea here, our sodium chloride is an ionic compound. That ionic compound as we're working, that positive negative is able to dissolve in the polar compound, but does not dissolve in the nonpolar compound. Little takeout idea for dinner time. We've got a little bit more oil again. We've got a little bit more water again. And this time what we're going to look at is using some soy sauce. Now soy sauce is made from water, soybeans, wheat, salt, sodium benzenate. If we take some of that soy sauce and put it in water, we can notice that soy sauce is basically just instantly dissolving and spreading throughout that. Whereas when we put that soy sauce into the oil, we can actually see it just kind of gelling up as little bubbles. If we go ahead and try to stir it in, it actually just breaks into smaller droplets. Whereas on the other side, that soy sauce is fairly evenly mixed throughout. So when we talk about that like dissolves like again, the polarity of the soy sauce is similar to the polarity of the water, causing it to dissolve. The polarity of the oil is different than the polarity of the soy sauce, so it does not dissolve in it. And a little coffee break for us. We've got some acetone and some water. So if we were to take acetone and water, we said was polar. If we were to put it in to our styrofoam cup, we notice that nothing is occurring right now. So it just kind of just sits there. So what we're looking at is that like dissolves like. The styrofoam cup must be a different polarity than the water for to not dissolve. The other chemical we have is acetone. Acetone is an organic solvent, so it's non-polar. And what we're going to look at is if we take and put some of the acetone into the cup, that quite a bit of a change has occurred so far. We can actually take and look and see that that acetone is actually dissolved and broken down that cup. So you wouldn't want to use a styrofoam cup for holding that acetone. So as we're looking at that, organic solvent is able to dissolve it. And our last one I'd like to look at is we've got some Mountain Dew. And what we're going to do with that Mountain Dew is Mountain Dew has carbon dioxide dissolved in it to give us those bubbles. Now liquids have gases dissolved into them. A very popular example of that idea is how fish survive is they use their gills to breathe oxygen that's actually dissolved in the water. What I'm going to do is just move all that liquid towards the top. And we're going to close that syringe. And what we'll do is, as we pull the volume back, that pressure decreases. So as we pull the volume back, you can start to see more and more bubbles come out of solution. Now if I open it back up, you can hear that gas coming out of solution. We can actually close the syringe back up. And this time when I pull open the syringe to make more volume, you can see that pressure is decreasing, allowing that gas to come out of solution. Gases are much different in the fact that pressure affects the dissolving. The more pressure, the more gas can be dissolved. So if we pull, we're actually increasing the volume, so it decreases the pressure, so less gas is actually dissolved in the solution, and we can continue to pull more and more of that gas out of solution every time we increase that volume. So pressure directly related. More pressure, more gas dissolved. The less pressure, the more gas comes out of solution. So just to recap some of those ideas for today, we're just going to go over to the board on the side here and just look over for the ideas that oil and water, non-polar, polar, likes dissolves likes. So oil and water don't mix with one another. The other idea was that collision with the solute and solvent to make those. So our time for T, kinetic molecular theory, the idea the faster the particles moving, the more collisions affects solids and liquids, doesn't affect gases. From there, life is a cube. More surface area increased, more collisions, causing the solute and solvent to come in contact, allowing us to have more dissolving. If we stir or agitate materials, they're causing an increase in collisions between the solute and solvent, causing an increase in rate of dissolving. Our world of salt, sodium chloride, the idea with sodium chloride, that positive negative dissolves in a polar substance. So again, like dissolves like. Time for takeout, polar dissolves polar, so the soy sauce dissolved in the water did not dissolve in the oil, the non-polar substance. Looking at a styrofoam cup, water did not dissolve in the styrofoam cup, so the water is polar. The styrofoam cup must be non-polar. That acetone, an organic non-polar substance, dissolved the styrofoam cup with that like dissolves like. And finally, our last one, using that syringe, the idea that pressure affects gas. The more pressure, the more you can dissolve. By decreasing the pressure, by increasing that volume, the gas came out of solution. Deal with that as Henry's law. Henry's law, the solubility of a gas directly proportional to the pressure that it's applied. So getting close to being out of here. Just wanted to go through and describe those ideas of solubility and effectors affecting dissolving today. Safe travels to everyone.